Well, hello everybody, and welcome to today's session. So, we have a very interesting topic in mathematics today that we're going to discuss. And I've repeatedly told you over time that there are two subtopics, or basically two sections of mathematics, which are extremely scoring from the exam point of view, and they are coordinate geometry and vectors, right? So, every time coordinate geometry or vector comes up, any topic from vectors come up in the session, I will mention this point because I want you to understand this fact, right? That these are free marks for everybody. So especially vectors. So we'll be taking up a topic from vectors today, and that's essentially I'm giving my own name to it because I'll be discussing three different cases or three different types of models in this, and this is the best I could name the theory. So basically we're in vectors right now, right? And in this what we're going to discuss is distances regarding planes, right? So primarily a distance of a point from a plane, from a 3D plane, right? So this plane is basically three-dimensionally spread out in space. So like distance between two, if you have two such planes, what is the distance between two planes? If you have one point, what is the distance of that point from the plane? And if you have one point, what is the image of the point in the plane? Like these are the three things that we're going to primarily discuss. So first thing is distance of a point from a plane. Right. So you have a plane. Let me call it ax plus by plus cz plus d equal to 0, or you can also say ax plus by plus cz equal to d. So I'll be calling it plus d equal to 0. Doesn't matter because d is anyways a constant, right? And let me write this plane vectorially also. This is the Cartesian form of the plane, right? What is the vectorial form of the plane? Vectorial form of the plane is nothing but r bar dot n cap is equals to d, right? What is n cap? N cap is, so this is r bar dot n cap, a unit vector along the normal to the plane, right? That's your n cap. And dotting that with r, what I'll get is d. D is the distance of the plane from the origin, right? If this is n cap, then d is the distance of the plane from the origin. But if this is not n cap and some n bar, then you'll have to divide d with mod n, and then you'll call that as the distance, because this is something that we've already discussed in planes, right? So I won't be discussing that in detail. So let's see. So first we'll solve this problem vectorially, and then we'll go into the Cartesian form of it. So you have the plane. Its equation is nothing but r bar dot n bar is equals to d. So remember, this is n bar. Because this is n bar, this d won't be the distance from the origin. To make this d the distance from the origin, I'll have to make this n bar n cap. So basically, I'll have to divide on both sides with mod n, and then d by mod n will be the distance from the origin, right? This is something that we have already discussed in planes. Like when we discussed plane in one of the sessions, right? So just watch out for that video. You have a point P in space whose position vector is given by a bar. What do you mean by position vector? If I start from the origin and I go to this point P, the vector that will join the origin to the point P, pointing towards P, is called a bar, right? And that's basically the position vector of P. What I want is, if I drop a perpendicular on this plane, what will be the distance of this perpendicular? That's all that I need, right? So it's pretty simple doing this basically. So what you have to do is, let the foot of the perpendicular be m, right? So the foot of the perpendicular, this point P, this point on the plane, which is the foot of the perpendicular, let that be m. So what if you do is, write the equation of Pm. So Pm is basically a line which passes through the point A and passes through M, right? How do you write its equation? So to write the equation of a line, I need two quantities. One is the point on the line, the other is the dr's of the line, right? Dr's of the line, or some direction to which the line is parallel. So n bar is the direction along the unit vector, or along the vector which is perpendicular to the plane, right? So can I say that Pm and n bar are in the same direction? Obviously, right? Because at the most you'll have a negative sign for n. That's all that can happen. But ultimately Pm and n will be along the same line, because n is also perpendicular to the plane, n bar, and Pm is also perpendicular to the plane. So I can write the equation of Pm as point which is a bar plus lambda times n bar, right? Because the plane is perpendicular. Now this is the vector equation of Pm. Now the point here being, what I can do is, this M lies on the plane. So this a bar plus lambda n bar has to satisfy the equation of the plane, right? If I take this as the thing, yeah. So how you go about this is r bar dot n bar is equal to d, and that this has to satisfy the equation of the plane. So a bar plus lambda n bar, which is your r bar dot n bar, is equals to d. Solving this, you'll get the value of lambda to be d minus a bar dot n bar by mod n square. So I hope you have understood this. So with this done, you can actually find out. So basically your r bar is nothing but a bar plus lambda n bar. What is r bar? Basically the position vector of any point on the plane, right? That's what r bar was. So essentially Pm is represented by this, and what is this? This is some r bar, and each of this r bar is on the line. That is the thing. And I need that lambda which is not just on the line but also on the plane. So that's why I substituted this in the plane, and then I got the value for lambda. So finally the r bar, which is the position vector for M, is nothing but a bar plus lambda times p bar, and the lambda that I got is this. Or mod n square times n bar. Yeah. This is essentially r bar, the position vector of this. But now what I need is, I need the segment Pm bar, which is nothing but OP bar minus OM bar. Or if you take, okay, so this is Pm bar, right? So starting from P going to M, so this is OM bar minus OP bar, not OP bar minus OM. If it was MP bar, then it would be reversed. So OM bar is nothing but r bar, which is your position vector of M, a bar plus d times minus mod a dot n by mod n square times n bar, and OP bar is nothing but a bar itself. So a bar will get cancelled, and then this is what you get for Pm. Now if you need the magnitude of this, it's nothing but the magnitude of this, d minus a dot n divided by mod n square, into n bar inside the mod, right? This entire thing is and this also will become mod, and this mod and this will get cancelled. So ultimately what you'll have is d bar minus a dot n divided by mod n square, and mod n will get cancelled. This is the final length that you have. But most of the times this is in the Cartesian form, right? This is in the vector form. So vector form, this is the approach, this is how you have to do it. I hope you have understood the steps properly. But Cartesian form, how do you do it? It's very, very simple. This is basically the Cartesian equation of the plane. Let x naught, y naught, z naught be the coordinates of the point P. So to get the distance here, it's very simple. What you just have to do is put this point in the plane. So essentially do this ax naught plus by naught plus cz naught plus d, and then divide with the unit vector along the magnitude of the unit vector along the perpendicular. That's nothing but a square plus b square plus c square. And essentially you can have a plus or minus here, but ultimately if you just need the distance, it's mod of this, right? Mod of this. So that's essentially the distance of the point from the plane. This constant that you see here. And I'm not deriving this in detail, but it's very easy to derive. You can also find the coordinates of this point M, right? How do you do that? Essentially, this is the distance of this point P from the plane M in the Cartesian form. And I'll actually show you how to find the coordinates of this point M. It's very simple. So you write the equation of a line in symmetric form. Essentially, this is x1, y1, z1. And x, y, z is the coordinates of the point M. So essentially what you do is x minus x1 by, let the dr's of this line be a, b, c, y minus y1 by b, z minus z1 by c. This is called the symmetric form, and I've already explained this in the 3D straight line video, so just watch that. This is equal to lambda, so you write x in terms of lambda, you write x, y, z in terms of lambda, some constant into lambda, some constant into lambda, some constant into lambda, right? K1, K2, K3. Now this x, y, z satisfies the plane. So essentially what you do is you put this in the equation of the plane, which is this, right? You put this in the equation of the plane, you get the value for lambda, and that's from there you'll get the value of x, y, z. That's how you find out the coordinates. So I'm not giving you the formula. There is a formula for the foot of perpendicular, which is very simple to remember. So just look at that formula in the textbook. But I would focus more on the understanding here. So I'm not giving you that formula. Moving on. We'll also have to discuss the image of a point in a plane. Make some space for you. That is the second distance that is associated with a plane, between a plane and a point, to be more precise. So that was my case A. The second case is if I have a point P, and now I'm not discussing the vectorial form because we can always convert between Cartesian and vectorial. So vectorial was something to give you an understanding of how to deal with vectors, but don't think that it's so that you don't think that it's very complex. It's very simple. But more often than not, we'll be dealing with the Cartesian forms, and you might get questions on the vectors form also directly. So just apply this simple understanding that I gave you as to creating the equation of a straight line and then satisfying the straight line's point of intersection in the plane. That's essentially what we do in the Cartesian system also. So this is how my plane was. This is the point P. X, Y, Z are the coordinates of the point P. Ax plus by plus cz plus d equal to 0 is the equation of this plane. I need the image of this point, which is P dash. What do you mean by image? If I go perpendicular, if I drop a perpendicular on the plane, and drop and move in the same direction along the same distance as to this, then the point that I arrive at is called the image, right? How do you get the image? So it's very simple, and I'm telling you in the Cartesian form. So let x1, y1, z1 be the coordinates of the point P. Let this be the equation of the plane, and now what you need is the image. So let x, y, z be the image. You can get the foot of the perpendicular, which is m, very easily. How? M is nothing but the midpoint of P and P dash. So the coordinates of M are x plus x1 by 2, comma y plus y1 by 2, comma z plus z1 by 2. Right. Also, there is one more thing. I can write, or in fact, you can do it this way. So now what you can do is you can substitute this m in the equation of the plane, right? And since you already know x1, y1, z1, you'll have an equation, but you'll have three unknowns obviously. So this alone cannot help you satisfy that, find out the, coordinates of the point P dash, because x, y, z is essentially what you have to find out separately, right? So to find out the coordinates separately, it's always better to do it in the symmetric form, right? So what I'll do is, I'll write the symmetric form of this line. So there are 2 points x1 and x on this. So essentially x1, or I would say x minus x1 by a. Because why a? Because a, b, c are the drs of the perpendicular of the plane, and this line is also perpendicular to the plane, so both of them will have the same drs, right? So I can just divide with a is equal to y minus y1 by b is equals to z minus z1 by c is equals to lambda. From here what I'll do is, I'll create this point x, which is a lambda plus x1. I'll create the point y, which is b lambda plus y1. I'll create the point z, which is c lambda plus z1. Now what will happen is, x, y, z, it is just having one unknown variable, one unknown parameter, which is lambda. If I can get lambda, I'll get x, y, z separately. So what I'll do is, in this equation, in this m, I will substitute x as a lambda plus x1, I'll substitute y as b lambda plus y1, I'll substitute z as c lambda plus z1, right? And then I'll substitute this m in the equation of the plane, and then my equation will just have one unknown, which is lambda. I'll find out the lambda, I'll put it back in this, and I'll get x, y, z, which is the coordinates of the image of the point. So that's how you solve for an image of the point. And if I ask you what is the distance of this point P dash, it is nothing but 2 times Pm, right? And Pm is something that you already know. Pm is something which is pretty simple. It's mod ax1 plus b. So just put the point in the plane, by1 plus cz1 plus d, and then divide with under root a square plus b square plus c square. This is Pm, perpendicular distance. Twice of that is Pp dash, right? So it's very, very simple. Coming to the third case. So third case is distance between two planes. So before answering this case, it's important for you to analyze when will two planes have some distance between them, right? So if the planes are not parallel, so if these are two planes, right? If they're not parallel, if this is bent like this will intersect this plane, because planes are infinite, right? So they will definitely intersect at some point or the other. So then I cannot say that the planes will have some distance, because the distance between them will be 0 once they intersect. So once two lines intersect, there is no meaning of the question. The question as to what is the distance between those two lines has no meaning when they intersect. Only when two lines are parallel, I can talk about this distance between them, right? So similarly, only when two planes are parallel, I can talk about the distance between them. So two parallel, just the way two parallel lines differ by a constant. So if I have a line ax plus by is equals to k1, a line parallel to this will be nothing but ax plus by is equals to k2, because both the lines should have the same slope, right? So they'll only differ by a constant. Similarly, if I just extend the same concept to 3 dimension, two planes will only differ by a constant. So if this is my first equation, first plane, ax plus by plus cz plus d equal to 0 or d1 equal to 0, the second plane will be ax plus by plus cz and only differing by a constant. And the moment you see two such planes, you can say, okay, these two planes are parallel, because they're only differing by a constant. And only then you can talk about the distance between them. So once again, the distance formula for them is very, very simple. The distance between these two planes is the difference of these constants divided by under root a square plus b square plus c square. So it's very easy to derive this also, but I'm not spending time on that because we have covered enough theory. How you do is, you just assume a point on the first plane, let that be x1, y1, z1, and then x1, y1, z1 has to satisfy this. Then move perpendicular to this plane, first plane, and go to the second plane and find the foot of the perpendicular, and then essentially find the distance between these 2 points. And this is what you'll get when you derive it. So I would suggest derive it yourself because it will help you improve your understanding. But anyways, the formula is pretty simple. The denominator is the sum of the squares of the dr's of the normals to the plane, just like this. But the only thing that differs is here you have a distance, here you have a difference of the constants, and here you'll have to put in the point in the plane and then take that value, right? So understand the distance differences separately, and the formula separately as well. So with this we are done with the discussion of the theory. So we'll discuss 4 to 5 problems now, which I find quite interesting in concept building. Let's proceed. So the question goes like this, the first one. Find the length uh, find the length and the foot of perpendicular from the point 7, 14, 5 to the plane 2x plus 4y minus z is equals to 2. Right. So let's draw the diagram for a proper understanding. You have a plane whose equation is 2x plus 4y minus z is equals to 2. You have a point which is 7, 14, 5. You need to find the foot of the perpendicular m. You need to find out the coordinates of this point m, and also you need to find this distance, right? That essentially is the problem. Now, I already told you distance is a very simple formula. Just put this point in the plane. So let this point be Pm. So Pm has a very simple formula. Pm is nothing but mod of, put the point in the plane, 2 into 7 plus 4 into 14 minus 5 and minus 2, like bring that equal to 2 on this side. You have to create this form. To apply this formula, the plane has to be in this form, like this has to be 0 here. So you'll have a minus 2 also, divided by under root a square plus b square plus c square. A is 2, 2 square plus 4 square plus 1. This is nothing but 14 plus 56 minus 7 divided by under root 16 plus 4, which is 20, plus 1, which is 21 root. So 56 plus 14 is nothing but 70, right? And 70 minus 7 is nothing but 63. So you have 63 by root 21. But this was pretty simple to solve for. Now, how do you create this point m? How do you get the point m? So very simple again. Let this point have the coordinates x comma y comma z. Now write the equation of the straight line MP. How do you write the equation of a 3-dimensional line? Difference of 2 points x minus 7 x coordinates divided by a unit vector or dr's of this line, right? What are the dr's of this line? Because this line is perpendicular to the plane, the dr's of the plane perpendicular to the plane ABC are the dr's of this line, right? So dr's of this line are nothing but ABC. So you have x minus 7 by a, and a here is 2. You have y minus 14 by b, which is 4. And you have z minus 5 by minus 1. 2, 4, minus 1 are the DRs of the perpendicular to this plane. This line is perpendicular to this plane. So 2, 4, minus 1 are the DRs of the line also. Right? That is what the whole point is. This is equal to lambda, some constant. I've created the equation of MP. Get XYZ in terms of lambda now. It is 2 lambda plus 7, 4 lambda plus 14, minus lambda plus 5. Now, x comma y comma z very evidently lies on the plane. So x comma y comma z has to satisfy this equation, right? And what is x comma y comma z? I just have that in one variable now, which is lambda. So instead of x, y, z, I'll substitute these in this. So 2 into x, which is 2 lambda plus 7, plus 4 into y, which is 4 lambda plus 14, minus z, which is minus lambda plus 5. This has to be equal to 2. So I have 4 lambda plus 14 plus 16 lambda plus 56 plus lambda minus 5 is equals to 2. They are collecting the coefficients of lambda, which is 4 plus 16 plus 1. And sending all the constants to that side, I have 2 plus 5 minus 56 minus 14. So hoping that I have made no calculation error here, the lambda that I get is nothing but nothing but minus 3. And I would like you to check the calculation again. This is minus 3. So I've got the lambda that I need. I'll substitute lambda in this now to get x, y, z. And what is x, y, z? The coordinates of this point M. That's all that I need. So x, y, z here on substituting lambda is nothing but 2 into minus 3, which is minus 6 plus 7, which is 1, minus 12 plus 14, which is 2, and 3 plus 5, which is 8. You have 1, 2, 8 as the coordinates of the point M. This is the method, right? It's very, very simple. You just know how to write the symmetric form of a line. So, moving on to the next problem. So here is your first problem. Now the second problem. Find the locus of a point the sum of squares of whose distances from the planes x minus z equal to 0, comma x minus 2y plus z equal to 0, 2y. Let me write it again. X minus 2y plus z equal to 0 and x plus y plus z equal to 0 is 36. So you have one point and there might be many such points. Every point whose perpendicular distances from these 3 points, from these 3 planes add up to 36 is what will form a locus. Locus is nothing but a shape which is determined by a specific condition, right? So every point which satisfies that condition will lie on the locus, and collection of all such points will make the locus or a shape, right? So what is the condition here? Any point on that locus, if you pick up, if you calculate its distance from one plane, second plane, third plane, add these 3 distances, it has to be 36. It has to add up to 36, right? That is the condition. So let my point be nothing but x comma y comma z, or let alpha beta gamma be a point on the locus. This is the solution. Be a point on the locus. So always any problem related to locus, whenever you come across any problem related to locus, first assume a point on the locus, right? And then put the point in the condition, solve the condition, and then replace. So like here I have assumed alpha beta gamma, I'll put that in the condition, solve the condition, and then replace alpha beta gamma with xyz, right? That is basically how to approach a locus problem. So distance from the plane x minus z is, I'll just put this point in the plane, alpha minus beta mod divided by under root 1 square plus 1 square, which is this, right? For this plane, the distance. This has to be added to the distance from this plane, which is nothing but alpha minus 2 beta plus gamma by under root 1 square plus 2 square plus 1 plus alpha beta gamma to be put in this now. And what we'll have is alpha plus beta plus gamma mod divided by under root 1 square plus 1 square plus 1 square, and this has to be 36, right? So and not just this, actually the sum of the squares of these distances from the planes is 36. So not sum, the condition is the sum of the squares of this. So I'll just expand this now. I have alpha square plus beta square minus 2 alpha beta by 2 plus, expanding this, alpha square plus 4 beta square plus gamma square plus 2ab plus 2bc plus 2ca, right? So minus 4 alpha beta plus 2 alpha gamma minus 4 beta gamma by 6 plus alpha square plus beta square plus gamma square plus 2 alpha beta plus 2 beta gamma plus 2 alpha gamma by 3 is 36. So solving this, it's pretty simple to solve. So I won't be stressing more on this. Just expand this, solve this yourself, and then what you'll finally get is alpha square plus beta square plus gamma square is equals to 36. Finally, this is what you get, and what you have to do in the end, replace alpha beta gamma with x, y, z. So what you're getting is x square plus y square plus z square equal to 36. The locus of these points is nothing but a sphere. This is the equation of a sphere, right? How will the sphere look like? The sphere will be centered at the origin, and it'll have a radius of 6 units, because this is r square, right? So any point on the sphere, if you pick up any point on the sphere, then that will satisfy this condition, because I've got the equation of the sphere from the condition, right? So that is how you do a locus problem. So with this done, we move on to the next problem. Yeah. So I would like to do this problem now. It's pretty simple and straight away formula based. So you have two planes, x plus 2y minus 2z plus 1 is equals to 0, and 2x plus 4y minus 4z plus 5 is equals to 0. Find the distance between these two planes. Now the first question is, whenever I talk about, so the question is find the distance between these two planes. So the question is, when do I talk about, or when can I talk about the distance? You can only talk about the distance between two planes only when the two planes are parallel, right? Do they look parallel to you? Are they parallel? So the question is, this is the drs of the normal to this plane are 1, 2 and minus 2. The drs of the normal to this plane are 2, 4 and minus 4. They seem to be different, right? So you would say that the planes are not parallel, they will intersect. And then I can't talk about the distance, but no. No, they have the same drs, because you can write the second plane as, you can write the first plane as it is x plus 2y minus 2z plus 1 equal to 0. And the second plane can be written as x plus 2y minus 2z plus 5 by 2 equal to 0. So you can obviously reduce this 2, 4, minus 4 in the simplest ratio of 1, 2, minus 2, right? And it's always written in the simplest ratio, right? The dr should always be written in the simplest ratio. So these two lines are obviously parallel. So the distance between them is nothing but the difference of their constants, which is 1 minus 5 by 2, divided by the square of the drs of the normal to the plane, which is 1 square plus 2 square plus 2 square. And that's nothing but 4 plus 1, which is 3 under root 9, right? And this is 2 minus 5, which is mod of 3, mod of minus 3 into 1 by 2. So the distance essentially is 1 by 2 units, right? So this was a simple problem again. Moving on to the next one. So this is one beautiful problem and a very, very important problem from the exam point of view. Find the image of the line x minus 1 by 9 is equals to y minus 2 by minus 1 is equals to z plus 3 by minus 3 in the plane 3x minus 3y plus 10z minus 26 equal to 0. Right. So, this is what you have to do. Find out the image. So, whenever there are image problems, what do you mean by image basically? This is the plane. If this is your line, when you project this line on the plane, how will it look like? That is what is called the image, right? Sometimes when the line is tilted, its image will be like just project a shadow and look at the project light from top and look at the shadow on the plane. That's what the image is, right? So the line can be tilted or the line can be perfectly parallel to the plane. So let's discuss about these two cases briefly and then go into the problem. So I'll say this is the easy case and this is not as easy as, this is 1, this is 2. I will say this is not as easy as 2. 2 is extremely easy. Why? Because when you project a shadow, the shadows of the line will be absolutely parallel to the actual line because there is no tilting or anything. The line is absolutely straight. It's completely parallel, right? So the shadow will also be completely parallel. And then what you have to do is just locate one point on the line, find its foot of perpendicular because they are parallel. These two planes, plane and the line, and these two lines are parallel. Just find the foot of the perpendicular. You'll have a point. You'll have the direction because you know the direction of this. So indirectly you know the direction of this, right? So you have the point, you have the direction, you can write the equation of a straight line right away. For this case, second case, this and this, as you can very easily see, they don't have the same direction. So in that case, sometimes what you have to do is, you have to locate 2 points on this line, find their foot of perpendiculars for 2 points, and then basically use 2-point form to write the equation of a 3-dimensional line. And that's something that I've already explained to you in the 3D line video. So let's look at what this line is out of these two cases first of all. So the drs of the perpendicular to this plane are 3, minus 3, 10. The drs of the line are 9, minus 1, minus 3. Now if you take the dot product of these two, so you'll multiply this to this, and this to this. So basically you have a 27 plus 3 minus 30, which is 0. That means if I have a perpendicular to the line, to the plane, the line is perpendicular to this perpendicular, right? That means the line is parallel to the plane. So just understand that. This is the normal, this 3, minus 3, 10 is perpendicular to the plane. But this is also perpendicular to the line. That means line is parallel to the plane. That is what I mean to say. That means it is the second case. So second case is very, very simple now. Just pick up 1 point on the line. And I already have a point available with me, which is 1, 2, plus minus 3, right? Z minus of minus 3. So I already have the point available with me, which I would like to project, and that's nothing but 1, 2, minus 3. How do you find the foot of the perpendicular? It's very, very simple. Construct, let x, y, z be the foot of the perpendicular. Write the equation of, this is P, this is M. Write the equation of MP, right? That's nothing but x minus 1 by. And what are the drs of this perpendicular? Nothing but the drs of the perpendicular to the plane, because this is the perpendicular to the plane. So that's nothing but 3, minus 3, 10. So you have a x minus 1 by 3 is equals to y minus 2 by minus 3 is equals to z plus 3 by 10 is equals to lambda. So x is nothing but 3 lambda plus 1, y is nothing but minus 3 lambda plus 2, z is nothing but 10 lambda minus 3. Now this xyz has to satisfy the plane because m lies on the plane. So essentially you'll put this xyz in this equation of the plane, right? So you'll have a 3 into x, which is 3 into 3 lambda plus 1, which is 9 lambda plus 3. You'll have a minus 3 into y. So you'll have a plus 3 lambda into minus 6. And then you'll have a 10z. So 10 into 10 lambda plus minus 3. So you'll have a 100 lambda minus 30 minus 26 equal to 0. So this is 9 plus 3, 12 plus 100. So 112 lambda. Send all the constants that side. So this is 30 minus 26, which is 56, which is plus 6 is 62. So minus 62 plus 3, which is minus 59. And when you send it that side, it will be 59. 36 plus 6 is okay, so 36 plus 26 is 62. Yeah, and 62 minus 3 is 59. So lambda is nothing but 59 by 112. Now you have the lambda. Put lambda in x, y, z to get the point. And right, when you put lambda in x, y, z, the points that you'll get are, let me write it straight away here. Let me write the point itself. It's nothing but 5 by 2, comma 1 by 2, comma 2. So now you have the point put a perpendicular available with you. You have the direction, which is 1, minus 2, which is this, the line equation of the line, 9, minus 1, minus 3, right? This and this have the same drs. You have the drs, you have the point, and when you have both available with you, you can obviously write the equation of the straight line, right? So it's nothing but x minus 5 by 2 divided by the dr of this line, which is 9, is equals to y minus half by the dr of this, which is minus 1, is equals to z minus of 2 divided by dr of this, which is minus 3, is equals to lambda. This is the equation, the image line, right? So do check for the calculation mistakes, because I had less space with me. So when you have less space, it obviously happens that you might end up ignoring some numbers. So just check out the calculation yourself, but this essentially is the method, and I wanted you to understand what the method is, right? So with this, we end the session, and I hope you found it worth learning about the lines. So about distances pertaining to planes.